We are here today because we are all interested in blizzards. And tonight we're so lucky to have the amazing Cyrena Arnold, a meteorologist who came to New Hampshire. She was the director of the Summit of Operations for Mount Washington Observatory, and she was also the New Hampshire One News TV meteorologist. She has been very busy working in all sorts of fields. And right now she is the director of product marketing at Atmospheric G2. But in her spare time, Cyrena is no slouch. She's done all this work while also volunteering as a STEM educator, giving presentations and keynote speeches across New England and helping kids get comfortable with weather. She wants kids to know that when she was in school, she really struggled in math, and then she went on to obtain a meteorology and a math degree. And she's written some kids' books about the weather. You can look for them on her website, which we'll put in the chat. And I love this last couple of facts about Cyrena. In 2022, she was Mrs. New Hampshire. I love that, Cyrena. And she's also a storm chaser and is a host of the Storm Front Freaks podcast. Cyrena Arnold, we are so happy to have you here, and we're excited to hear all about New England blizzards. Thank you. Cyrena, you got
There we go. It says I'm muted. There we go. Technology 101 here. Well, thank you so much for having me. Like it's such an honor and a privilege to be a part of the Harris Center. I love the Harris Center. My kids do the programs there that you offer in the summertime. And I'm just such a huge believer in what you guys do and love what you guys are doing for nature and STEM. So it's great. Let's talk about some snow though, right? That's kind of what we're all here for. So we're going to talk about New England blizzards and a whole bunch of different stuff around those topics. So let's just dive in and like get going here. So we'll start off with kind of a why me? Why am I talking to you about this? And then we'll talk the science behind the storms. We'll talk about past storms. We'll talk about our changing climate. And then we'll also get into the winter predictions for this year, because I know that's kind of what ultimately what we're most interested in, right? I think that's like the final thing that's so amazing and interesting. So that picture there is little tiny me. And the picture to the right is the first tornado I ever saw. And that's what got me hooked on weather. And I just thought it was the coolest and craziest thing that I had ever seen, and was like, well, this is absolutely amazing. So I've spent the rest of my life with a good, healthy obsession with the weather ever since then. And so I got to work with the National Severe Storms Laboratory, with Smart Radars and the History Channel. I've worked with NASA contractors. I worked at the home of the second world's worst weather in Alaska, doing air quality monitoring in some really remote locations, which took me to the Mount Washington Observatory, and had a lot of fun there, and got to talk about weather on international TV and on an international stage. NH1 News, when they were around, and gave MUR a run for their money for about 2.5 minutes. That was a real fun opportunity, and I enjoyed that. And I've been kind of more in the corporate world now, working with insurance companies mostly, helping them understand weather, and recently just moved into energy. So Atmospheric G2 is an energy data provider, and so really happy to be working with them and working with renewables and stuff like that. I've written 2 children's books, The Weather Story and The Hurricane Story. I do a lot of weather stuff on social media. I'm sure there's some people here that are from the social media worlds that I do. So if you are and you came here from social media, give us a shout in the chat and let people know. And then I've been privileged enough to be featured in a lot of different types of media, which is fun. And in fact, right now I'm coming to you from Manhattan. I just flew here from New Hampshire this morning. I'm going to get to add another logo to this list here after tomorrow, which is kind of fun and exciting. So love the weather and really love telling other people about it and explaining it. So let's talk about the science behind the storms here. There's a lot of different types of snowstorms. I mean, when it snows, you can get snow that happens in a lot of different ways, but snowstorms can happen in multiple ways. We get nor'easters, which are like the big storms. Those are the big, interesting snowstorms, the ones that make the news. Blizzards are a specific type of condition that are actually really hard to meet and very, very rare, and we'll talk about that. Snow squalls, really heavy downpourings of snow that last for a short period of time, whiteout conditions. Lake effect snows, which give you the snows that you can measure in feet on the east side of Lake Ontario and Lake Erie, and really on any large body of water. And then we have clipper systems. And all of these different types of systems come from these different masses that you see here. And so clipper systems come more from Canada and are colder in origin and drier with less moisture, where nor'easters are actually the meeting of that cold polar air with the warm tropical air, and how that interacts and creates this deep area of low pressure and cyclogenesis and stuff like that. So when we talk about snowstorms, there's a lot of different ways that we can quantify them. And we'll break down some of these here as we go. So one of the most interesting things about weather is understanding pressure, because pressure is actually what drives a lot of our different weather. And so this is an excerpt from the weather story, helping people to understand the difference between high and low pressure. And we've all seen it on the news. When you see the TV meteorologist, there's the big red H and the blue H and the red L, and it's like, well, what the heck does that mean? They seem to think it's significant, but nobody seems to share that. If you were to think of columns of air pressure, like cylinders, like you see here, it helps you to understand kind of how our atmosphere moves and is really the basis for everything. And so in the weather story, we say the air above us is heavy, which you might never know. Its pressure pushes us every day and can be high or low. High pressure brings the sunshine and keeps the clouds at bay, but rainy, cloudy, windy days mean low pressure is on the way. And the whole reason that this happens is if you were to imagine joining these two cylinders with a straw, I use my mouse right down here. Say you were to put a straw between these two and join them. What would happen? They would try to even out. The cylinders would try to be the same height. The high pressure cylinder would drop, the low pressure cylinder would rise. And that tells you everything you need to know about how the atmosphere moves, because in high pressure, you have sinking air, which causes drying out, warming, evaporation, which is why high pressure days are typically cloud free. And low pressure storms is rising motion, it's cooling, it's condensation. And so all of our weather happens simply from pressures trying to balance each other out. That's everything. Wind is what happens in that tube. All wind flows from high to low pressure all the time. And so when you understand this basic concept, it helps you to understand how all of our weather systems work and how weather drives and thrives. So in order to get snow, we need low pressure systems. We need rising motion. We need condensation. We need cooling. And we need clouds to form. Having said that, we have a lot of different jet streams. And it's probably a term that most people have heard here. We have four prominent jets that happen around the globe, two in the northern hemisphere and two in the southern. And the jets are really essential part of our weather. So we've got like a polar jet and a subtropical jet. And one of the things that's really critical about snowstorms is understanding where that jet stream happens, because the jet stream is almost like a bowling alley for storms, that wherever that jet stream sets up, that's the path that low pressures and storms are going to take. And the reason this happens is because as the jet stream moves along, you can actually see that where that jet is, where you see this purple one here, you have the air that's coming together at the surface of an area of low pressure and rising right where this jet occurs. And the jet is a very fast moving airstream located about 200 to 300 millibars, about 30,000 feet above the surface of the earth. And that very fast moving air causes divergence because it's moving so much faster than the air below it. Because it's moving so quickly, the air below has to kind of come in and fill that gap and fill that void, which increases the area of low pressure. And so this is why the jet streams and low pressure areas kind of always go hand in hand. Now, it's like a ball in a bowling alley. You may get a gutter ball, it may roll down off to a side, or it may go straight down the middle. But knowing where that jet is a really essential part of understanding what path low pressures are going to take. And if you were to map out the typical weather patterns across the United States, everything exits in New England. Some people call New England the tailpipe of the United States. I think that's kind of a harsh and unpleasant way to put it. I think it's much more pleasant than that, but it doesn't matter whether a storm originates in the Pacific Northwest or in the Southwest United States or the Gulf. It's passing over New England. And the reason is because of the jet stream and how it basically is always passing out over that direction. And the reason the jet stream always goes that way is because over the Atlantic Ocean, there's a semi-permanent high pressure that happens here. And high pressure rotates clockwise. And so our ocean rotates this direction. The atmosphere rotates clockwise around here. And so it's this constant steering current, almost like a wall for the jet stream, where it's almost always exiting over New England. And it's part of the reason why we get such good storms. The other thing that's a big driver in our storms is El Nino and La Nina. And so this oscillation of the equatorial Eastern Pacific sea surface temperatures, whole bunch of words for what's the temperature at the top of the water right there on the equator in that Eastern Pacific. If it's warmer than average temperatures, that's an El Nino. If it's cooler, it's a La Nina. And the reason these happen are because of the large scale wind currents. Typically, if the winds are really low over these regions, it allows those sea surface temperatures to stay still and the sun will warm up, they'll get very warm. But if you have a lot of wind happening over here, you get a pushing off of those sea surfaces temperature, like the warmer sea surface water. The water below it wells up, which is cooler, and that's how you get these colder temperatures. And these warmer and cooler temperatures and the winds that go with them drive a tremendous, tremendous amount of our weather. And this El Nino La Nina is probably one of the strongest correlations we have in order to look ahead and actually figure out what's going on with winter forecasts and actually talk about doing forecasts on a seasonal basis. And we track this, and it's been tracked. You can go to the Climate Prediction Center, cpc.ncep.noaa.gov or something like that. And if you dig through all the links, it's a government website. It's not the most friendly or beautiful thing in the world, but it is data heavy and it is loaded. And you can actually go back and take a look at El Nino and La Nina times back to about the 1950s. And so what we're looking at is about a deviation from normal plus or minus a half degree, and they're labeled in colors here. So if it's, cooler by a half a degree or more, you're seeing a La Nina and it's indicated in blue. If it's red, it's a Nino, and we joke and say if it's black, it's La Nada. And these are calculated by 3-month averages. So we kind of use the sea surface temperatures averaged over a 3-month time frame. So if you see the letters on here, you'll see December, January, February, March, February, March, April. So we're looking at kind of those 3-month clusters and using that average to determine what's going on. So this is a real nice way of getting a historical look at what's happened. And so you can see right now we had El Nino last winter, and we have fallen into La Nada. We're slowly trending Nina, but we're not quite there yet when you look at these numbers, and we'll talk about that more in a little bit. So nor'easters. Nor'easters are the big snowmaker for us. They typically occur between September and April, but really the strong ones and the good ones are November to March. And they can actually be responsible for a lot of damage. And the main reason is because they always affect that I-95 corridor, right? We're talking like Philadelphia, New York, Boston, right? We're talking some of the major populated locations of the eastern seaboard. And so you get a lot of things that happen. These storms develop somewhere between Georgia, New Jersey-ish. These low pressures come out to the ocean and then move up the eastern seaboard there and bring lots of heavy rain, snow, wind, flooding, rough seas. And because of the rotation, it's a low pressure, rotates counterclockwise, as you see here from this comma shape. The part that is over land is typically blowing from the northeast, which is why these are called nor'easters. And so the East Coast is it's like the perfect set of conditions for the type of weather that we get for these nor'easters. What we have is that polar jet brings that really cold, crisp air across from Canada. It meets that warm, humid air over the Gulf. Those things mix. The atmosphere is trying to balance itself out again. It's why we have the weather, and you get these storms that are created. And it's that differential of that cold air and the cold land and the warm water that really fuels these storms. So where we are is just kind of the perfect example. And you can see here with this image, this is an image showing sea surface temperatures. You see how with this clockwise rotation, we have how the warmer waters really funnel their way pretty far up the eastern seaboard here because of that. And so interesting tidbit and trivia fact for equal lines of latitude, the Atlantic and the Pacific, the Atlantic is 10 degrees warmer on average than the Pacific. And that has to do with the ocean currents and the rotation, which is pretty neat. So it's just an ideal spot for this type of weather. So I mentioned earlier the blizzard conditions, and this is where mentioning how specific they are is actually quite important. So in order for something to be a blizzard, you actually have to have winds sustained at 35 miles per hour or greater with blowing snow or falling snow that reduces visibility to a quarter of a mile for 3 or more consecutive hours. That's intense. I mean, we see blizzard conditions in here in New England every once in a while. And so I know the talk is talking about blizzards, but it is interesting and important to know just actually how rare they are. And so these are different types of winter weather warnings we can see in New England. We can get blizzard warnings. There's also ice storm warnings. Interestingly enough, for us, it's pretty high up here for a half an inch or more. If you look at what an ice storm warning threshold is for, say, Atlanta, Georgia, it's more like an 1/8 of an inch or maybe even a 1/4 inch. So the thresholds for these different warning criteria actually change across the country because we're New England and we can handle ice a little bit better than they can in a place like Dallas or Atlanta or something like that. Winter storm warnings, basically meaning that it's imminent, that you're going to get 7 inches of snow or more within a 24-hour period. So sometimes you wonder, like, why is it just a winter weather advisory versus a winter storm watch or a winter storm warning? Warnings mean it's imminent, and this helps you understand some of the criteria that happens with that. And there's also lake effect snow warnings and wind chill warnings. But watches mean that it may happen. And so there's a graphic. Actually, I should have included it here. I just realized there's a great graphic. You can imagine this. Pull out your imaginations here, where there's a cupcake watch and a cupcake warning. And a cupcake watch shows all the ingredients of a cupcake. It's like a bag of flour, sugar, some eggs, butter. And a cupcake warning is a photograph of a cupcake. And that's exactly what it means. Like, watch means it may happen, all the ingredients are there for it to happen, but a warning means it's imminent and it is actually happening. So the National Weather Service can issue outlooks a few days in advance, 3 to 7 days in advance. Once we fall to that 3 days to day time frame, they can issue watches. And then warnings mean that it's imminent. So that just helps you kind of understand some of the differences between the criteria of the advisories that get put out. Um, okay, so that's some of the science behind what's going on, why we get the storms that we do, and what the National Weather Service does. So let's look at some historical data. And we're not going to go through this like, hey, remember that big storm in 1980 something or other. We're actually going to look at this from a data perspective to look at past storms. And so our local National Weather Service office is the office out of Gray, Maine. And so they've got two really good sites for data, Portland, Maine, which we'll look at here, but otherwise we're going to focus on Concord. Just trying to pick that as sort of a central location. So know that if you look back and think and go, oh yeah, I remember that year, but it wasn't that crazy. Obviously it varies a little bit as we move around. But this is showing snowfall here in Portland, Maine, and showing you our top 10 snowiest winters. And look at that, 107, 102, 101 inches of snow as compared to the least snowy years where we're looking at 9.5, 19.9. That's a heck of a spread in possibility of the amount of snow that you can see. Now, the check marks that I put here, I put there just kind of for fun, because blue checks are La Nina years, black checks are La Nada years, and red checks are El Nino years. Because there's some correlations that, like I said, they're not super strong, but they're enough to where we use them a lot in forecasting. And that is that with La Nina years, and we'll dive into the science of this a little bit more, La Nina winters are typically more front-loaded with snow in New England. And El Nino years typically give us the bigger, later snows. Now, there's always exceptions to every rule. Just because it's a La Nina winter and typically it's front loaded doesn't mean you can't get a big March storm. In fact, there's a couple examples in here where that happens. But overall, and statistically speaking, that seems to be a pretty good rule of thumb for what we have here. So looking back and seeing some of these, if there's no check mark by it, it's past the time where we were monitoring that data, and so I don't have any data for historical La Ninas or El Ninos beyond 1950s. So seeing the 1930s and the 1800s, just don't have that information. But it's kind of fun to see the differences between the snowiest and the least snowiest years from 1991 to 2020. If we look for Concord, similar things where, the highest years, there's that one that's 102 inches. That's wild. But typically a good snowy year for us is somewhere in, the 70s. And on average, places around New England, it varies, obviously more the further north you go. But I know for like Concord, Manchester-ish, if you're looking at in the 40s or maybe 50s of inches for snow per year, that's pretty average. That's pretty good. And so you can see where kind of the highs and the lows correlate here for that. So I don't know if you're looking through these and being like, oh yeah, like I remember that, big snowstorm in 1981 and 82. Like I remember that was a really snowy year. That was crazy. I've only been in New England since 2012. And so the only one I remember is 2014, 15. And that was a great snow year. I had only been in New England 2 years and I was very excited thinking that's what winter looked like every year. And I have not been very pleased with the actual result ever since. I really enjoyed the snow. But 2014-15 was a great year for snow. And it's cool that you can see it here, make this data right here. So that's kind of fun. As for snowiest months, taking a look once again for Concord, seeing that, to get this amount of snow, basically your season's worth of snow in 1 month qualifies as a pretty snowy month. And that's pretty amazing. And if you look at the check marks here, it loosely correlates to what I was saying earlier, where the blue ones are typically the earlier season, but there's your March exception in 1956. Lanadas can happen at any time, and then the big late season snows typically happen later, and seeing the check marks here, February, and 1 January. So not surprising really to see that. It's kind of what the data supports for a long time. And the reason I keep mentioning this is because this is going to be a big part of our forecast for what's going to be happening this year. So looking through seeing some good events here. I definitely remember that February. That was a great year, a great month to go skiing. I think I did a lot of skiing in February of 2015. That was one of those years I got in like I think almost 30 days. That was nice. And then looking at some individual storms that we've seen around Concord, New Hampshire. And when these happen, I mean, they affect other areas too. They'll affect some of the North Country, and depending on the orientation of the nor'easters, some of these were big snows for Boston too. Some of these were more rain for Boston. It varies. So as you go around New England, you can see how that changes a little. So seeing snowiest days here, 25 inches, December 17th of 2020. Of January 12th of 2011. Both of those were Nina years. And then looking at over here, tops snowstorms, so not just a day's worth of snow, but looking at actual storms that could last more than a day. Same thing, early season. Look, I mean, here's an October one. Not surprising at all for a Nina year. October, December, January totally makes sense. A big February storm for a Nina year, El Nino year, excuse me. And then the Lenadas, they can kind of happen at any time. So it's kind of fun to see when those big snowstorms were, when they occurred, and just how much they gave you. And this was a fun chart I found too. So this is showing record snowfall by county. And so it lists the counties in New Hampshire over here on the far left side, the city that has the record, what day they had the record, and the amount. And so for Hillsborough, which is where I am, pretty cool to see in Francistown, 32 inches in a single day, February 10th of 2013. It's pretty cool to see. But how amazing that we're looking at one state, and you'd think that a big snowstorm would come in and would affect all of them. And it's amazing how hyper local it can be in some regards, because I see two here for 1969, and these two for 2018. There's two 1933s. There's not a lot of redundancies. It's not like half of these years are all one storm that came in and gave everybody their record snows. The way the meteorology sets up and gives you these big record snows can be very hyper local, and can be kind of interesting to see. So just kind of fun to look at this data and show people what historically is going on. So when that person comes to you and says, oh yeah, remember in 2015 we got 48 inches of snow, you can look at this and say, no, you didn't. You measured a snowdrift. So it also helps to kind of set the record straight too, and level set a little bit. What is a really good snow, what is a big snow. So so how are these how are these snows going to continue in a changing climate? Are we still going to expect them? Are things going to be changing? And that is a really big unknown that we have right now. And when you look at global temperatures, this picture on the bottom left shows you averages in temperature for a very long period. I think it's 1979 to 2023. And the highs and lows are within this gray area, and you see the average in the blue line. And the red line is what temperatures were for 2023. And so we're definitely seeing a tremendous amount of warmth. And if you look in the top right graph, the dark blue colors are the years are 1940s, and they kind of scale up through the shades of red to the most recent years for 2023. There's a trend. There's a trend. Things are getting warmer, and it's really apparent. But the reasons why can also be kind of interesting. The big jumps that we saw in 2023 are actually caused by a volcano. So I don't know if anyone remembers, in January of 2022, there was a very large underwater volcano, Hungatunga Haipai, that erupted, and it sent water vapor and ash and dust about 58 kilometers up into the atmosphere. Now, just so you know, the atmosphere has about 4 layers in it. There's the troposphere, the stratosphere, the mesosphere, the thermosphere. All our weather happens in the troposphere. Most of our water vapor is there and what have you. This sent water vapor into the stratosphere and even into the mesosphere, where water vapor just doesn't really exist, because this was such a large blast. And I think that's probably making everybody dizzy, and they're tired of seeing that loop over and over again. When this happened, it was very well forecast that this was going to have a tremendous impact on global temperatures. And so here's an article that came out 2023, January 12th of 2023, saying, it's going to be really interesting with what happens with temperatures here, because water vapor is a greenhouse gas. It got sent into the stratosphere. and into the mesosphere, where it can absorb more water, where it can absorb more heat and warms up the air around it. And so we know how greenhouse gases work, and we know water vapor is the most prominent we have one of our atmosphere. So it's like, wow, some interesting warming is going to happen here. And that's why when you look at these charts and look at temperatures for 2023, they were off the charts. And a lot of that had to do with that. But there's actually another reason too, beyond climate change. Oh, and here's a graph just showing, this shows water vapor in the different layers of the atmosphere. And this is what the water vapor did after that underwater volcanic explosion. So typically, volcanic explosions actually contribute to global cooling because it shoots so much particulate into the air, dust, ash, things like that, that don't let solar radiation come through our atmosphere, reflects the light back out, so things can't get as warm. But an underwater volcano eruption, which is much more rare, shoots the water vapor up and instead does the opposite effect and has a tremendous warming effect. So had this volcanic eruption happened on land and not been underwater, it could have helped with a global cooling effect, but it didn't. It did the opposite and sent all this water up. And it is very visible in data, in all the data. The other interesting thing about this is, so even with a warming climate, some people may or may not have heard the correlations. Or with a changing climate, with a warming climate, you get more temperature extremes. So global warming is kind of a misnomer because with climate change, you actually get bigger, colder extremes too. People are like, well, how in the heck can that happen? That doesn't make any sense. And the big thing is the polar vortex. And so the polar vortex becomes a buzzword on the news, and it's when those temperatures drop to like -40 and it gets really, really cold. And we have those every once in a while. But the polar vortex is actually always there. It's always up at the Arctic. It's constantly spinning, and it's like a spinning top. So think about a spinning top. And if you spin it and it's really spinning efficiently, it stays in one place. It's really good. What happens is that top starts to slow down. It wobbles, it meanders. It's not a tight spinning top anymore. It starts to wobble and loose, and Lord knows where it's going to end up. Stratospheric warming causes the polar vortex to lax and stop spinning so tightly. And when we get sudden stratospheric warming events, like that volcanic eruption, and there's other times that this happens as well, where the stratosphere gets very warm, it sends the spinning top into chaos and slows it down. And so when we get these polar vortex events, what you have happen is it's the breakdown of the spinning top, and you actually just have this, it starts wobbling up there, and the cold air pools, like you see in this right graphic, and starts coming down in places where it typically isn't at. And so this is why with a warming climate, changing climate, you also get more extreme cold events that happen, which is just a very interesting correlation. And so here's a graph that shows sudden stratospheric warming events. And back in the 18 or 17, words are hard, 1970s and 1980s, you could get a count on a polar vortex happening maybe every other year-ish. And in recent years, it's like an annual thing. And the reason it's happening more frequently is because of a warmer stratosphere, because that spinning top breaking down more frequently because of the warming temperatures and the frequency is picking up. So it's a very interesting thing that happens, and a very interesting correlation in our climate. Very wild. The other thing that's very interesting is we tried to do a really good thing and said, hey, these sulfur emissions from these ships that are happening are a really, really bad thing. We got to get rid of these. And after we did, temperatures went up a little bit, because turns out that the sulfur oxides were reflecting light back and helping to reduce some solar radiation. And by reducing this very dangerous pollutant, actually contributed to some slight warming in our atmosphere as well. And so this was also a big change that happened in 2022. And so not only did we have this reduction of sulfur oxide, but then we had this volcanic eruption that sent the water vapor into the stratosphere. And so we were at a very uncertain time in meteorology and in climate in some ways as well, because we have a lot of things happening that haven't happened in our lifetime before. And meteorology is a relatively new science, just as is in general. Forecasting has really only come around since about World War II, when they finally determined it was worth investing in because it could be a military strategic advantage. So it's really interesting to see how forecasting has changed. And we've had a lot of consistency up until kind of recently. And so how are forecast models going to handle this? And how do climate models handle some of these big changes that we haven't seen before and haven't modeled before? And there's a lot of research being done to figure out how many years is it going to take for the results of Hunga Tunga's volcanic eruption to actually stop warming things up again? At what point does all that water vapor make its way out of the stratosphere and stop affecting the weather? And the research is, we don't know. We're gonna have to see what it is, but some people say 5 to 10 years, some are saying 10 to 20. And so it's just interesting to see. And so with a warming climate, how's that going to affect our storms? Well, we're definitely going to be seeing less snow, unfortunately, because if the freezing line moves further north than it does. But even the plant hardiness zones have moved. So if you do any gardening whatsoever, they just recently updated these. And so if you look at the top two images, and I zoomed in on New England on the top right, from 1981 to 2010, see what zone you're in and see how that has changed when they had to update the maps and how things are moving. So before that sort of yellow area was a zone 6, you could find through most of Massachusetts, Rhode Island, Connecticut, except for coastal areas. Now, zone 6 goes up through the coast of Maine, the entire southern half of Maine, southern Vermont, and only really includes the western and northwestern half of Massachusetts. We're seeing almost an entire zone shift with this. And so it's not just meteorological, we're seeing it in all of the different types of earth sciences where there's impacts and changes that have to be made because of this changing climate. And so we're all kind of riding this roller coaster together, trying to figure out what this means for long-term changes. But I mean, if it's warmer, um, snow gets harder. And I know there's a lot of people, if you're here tonight and you're joining from like Connecticut or Rhode Island, one of the questions I get most from people in those states is like, when is it going to snow again? I mean, when's the last time you guys saw a really good snow? And if things are warmer, it just gets a little bit harder because right now you're dealing with weather that was a lot more like southern New Jersey, Delaware, and the Virginia coast 30 years ago. So it's an interesting thing to see. A winter prediction. So what does that take all that and bring that together and see what does that actually mean for this year? And I've got a lot of data and graphics, but I'll talk you through it, I swear. So it shouldn't be too terribly bad. The Climate Prediction Center says the La Nina conditions are most likely to emerge November through January is about a 59% chance, and then going back to neutral or nada by March or May. And so this graph shows where we're sitting with the little red dot. And these are all the different forecast models. And so it wouldn't be a strong La Nina, but I will tell you the forecast models have been saying since last spring, Nina's coming, Nina's coming, Nina's coming, and it hasn't. And if you look at these numbers in this little piece I have up here, I mean, we came out of El Nino and we've been sitting really in La Nada territory for a long period of time. And so will we reach Nina? Will we not? Has a big impact on actually on our forecast. As you saw from the historical storms, when you get your big snows is really going to be dependent on how that happens. So I've done a thing here, and I've compiled a lot of graphics, but this was really fun for me, where we looked at historical years. And so, what are the historical Nina, Nada, and Nino years? Try to say that 3 times fast. And OND is October, November, December. JFM is January, February, March. So we're looking November to February-ish. We're looking at like a 4-month time span. And looking back, the historical Nina years are listed here in blue. This one is just November to December for 2016. Like I put there's some specifics in some of these. And so I can go and create charts saying, all right, show me how temperature was different during these years and these months compared to all the others and the averages. And it provides these amazing graphics. And so what I've done is I've done this for temperature and I've done it for pressure. And I think precipitation as well, showing Nina, Nada, and Nino conditions. And so you can see just how crazy different some of these are. So I'll talk you through what we're looking at here and why this matters. Let me get this little box out of my way. Here we go. All right, so looking at November temperatures, if we're in a Nina year, things are typically warm, and this past November was warm, if you recall. If we're in Nada, we actually see some cooler temperatures typically in New England, and if it's Nino, we're looking about normal. Now, come December is when things change, and in Nina years, this is where our winters can get front-loaded, except with ignore Maine for some reason. They're gonna fall into the other part here. But generally speaking, for the northeastern United States and really almost the entire eastern seaboard, Nina years are colder in December than other years, and Nino years, as you see on the far right, are a lot warmer. And this really helps to contribute to what we see and know in meteorology is that La Nina years are definitely front-loaded with snow, And you're more likely to get that November, December, early January snowstorm, and not the end of season ones where Nino years, the warmer years, that's where you're more likely to get the February, March, God forbid, April storms. So you can really see these correlations here in that data. And as you start to come into January, look at the shift. So in a Nina year, we start warming up and getting above average temperatures, and come Nino, temperatures are starting to drop. The reason I mention this is because we're supposed to really fall into Nina, though we're still kind of hovering at La Nada. And so where I'm putting us for this time of year is looking somewhere around here, which means I'm thinking January is going to be probably a little bit warmer than what we would see on average. Which, if you're a skier like me, is not the greatest news in the world, but it's the news that we've got. February, unless you are up in the upper plains or in the Pacific Northwest, there it's going to be cold. But Nina, look at February temperatures for La Nina years in New England, compared to an El Nino year where things are typically cooler than average. And so just really good foreshadowing. Once again, if it's really warm, you can't get the big snowstorms, and for multiple reasons. One is, could be too warm for snow, but two, if you don't have that really big difference in the warmer ocean waters versus that cold air that's moving in, you just don't have that imbalance of high and low pressure and temperature in the atmosphere trying to balance itself out again. And so when you get this warmth, it just creates less storms for multiple reasons. And so even in a Nada year, seeing it be warmer. So once again, February, probably likely to be warmer than average. March, probably likely to be warmer than average, unless we stay in Nada, and then we could have a very interesting March surprise. Could be very interesting to see. But they're calling for us to go into Nina, and if it happens, great. But if not, and we get a big snowstorm in March, just saying, you can see what the data has to say. Pressure. Okay, so the warm colors are going to be higher pressure. The darker colors are going to be lower pressure. And so remember, high pressure creates drying air, warming, sinking air, no clouds. We need low pressure in order to have storms. We need low pressure for rising, for cooling, for condensation, for snow. So seeing a little bit more of that in November in a Nina year than we do in a Nino. And so, but this November was we knew our November this year was a little bit warmer than normal. We were also a little bit drier than normal this November, but that's okay. How does this change come December? Typically in Nino years, really high pressure over New England, which once again does not allow us to have these earlier season storms, but very favorable in a Nina year. And as we move into January, things start to shift a little bit. Still the possibility of low pressure into January, and Nino kind of falling right in between, a little combination here, still kind of medium for a Nino year. But we will start to see that shift. Now, February, high pressure starts to build in Nino years on the eastern seaboard, and we're starting to see more low pressure. Once again, this is why we get those big late season storms. And then forwarding into March, once again, big difference. Massive areas of low pressure typically over the northeastern United States come March. High pressure typically in March in a Nina year, and also in a Nada year. Precipitation, the blues are above average precip, the warms are below average precipitation. So seeing for November, mostly drier actually for most of the eastern seaboard. And that's kind of across the board for all of these years that we picked. But seeing a shift in December, a little bit more moisture tends to move in come December. Similar for January, a little more precip moving in for February, but if that's coming with warmer temperatures, that's rain, right? Like that's a rainy February, and that is not. I see Susie shaking her head no. She's like, yuck, I can see it from here. Double thumbs down. Yeah, and then March, a little bit drier than average, and so over here for a New Year, you're seeing typical. So all you got to get is a really good area of low pressure to come in, and that can definitely change that. So it's an interesting breakdown of looking at what the data has to say for those Nino, Nada years, and see what happens. So if you want to know like what a winter prediction would be, then is since we are La Nada phasing into La Nina, La Nina-ish. Hard words are very difficult sometimes. We're definitely more of an early winter pattern. We're definitely more into that. If we're going to see snows, I mean, look at December. December was nice. It was great. But come halfway through January, like it's not looking great for seeing late season snows. I think the end of winter is going to be warm. I think it's going to be dry. And there's also signals that actually our odds of having a polar vortex are very low with Nina years. I think it was something out of like the last 14 Nina years, only 4 have seen polar vortexes, but of a comparable number of Nino years, you see much higher. It's almost double digits as well. And so all the conditions aren't really coming together for us to see that big drop to like the negative 40 like we do see every once in a while. So it'll be interesting to see how it actually plays out, because I mean, it really is, it's an educated crystal ball that we have, but it still is a crystal ball. We're still forecasting, and forecasting is really hard and difficult. But my winter prediction is definitely more of a early season winter than late season. So not a lot of spring skiing probably in our future this year, unfortunately, unlike last year where it was really great because it was an El Nino year. The last thing that I'll end on then for this, and then we'll get to a couple questions, is with warming climates and changing climates, I think we're also more prone to see ice storms. And a reason being is this. So interesting tidbit number 2 from this that I hope people can walk away with and understand is that all precipitation on our Earth starts as snow, always, with possibly the exception of like maybe at the tropics in the heat of summer. Our summer storms here in New England start as snow. Everything does. It's just way, way up there. Temperature drops about 5 degrees for every 1,000 feet you go up. It does not take long to reach that freezing line. And so what determines whether you get sleet or freezing rain or rain is really what happens down close to the ground, but also more importantly, this mid layer of the atmosphere. And so you get snow when you have snow and it stays cold and it can fall as snow and everything's lovely. And we get rain when it starts to snow and it melts. But it's when we have this intrusion of warm air in the mid layers, which we're seeing more and more of, that you get more ice events. And the 2 different kinds of ice events we get are really sleet and freezing rain. And so sleet's when the ice pellets fall from the sky. And so the snowflake melts into a raindrop because there's just a little bit of warm air way up there, but it has enough time for that raindrop to freeze again before it hits the ground. And that's how you get sleet. Freezing rain, which we have seen a very interesting amount of in several winters in a row, happens because you actually have a lot more warmer air up above. So the snowflake melts into a water drop. It falls through a majority of the atmosphere, but the temperatures at the surface, due to cold air damming or a lot of other reasons, are below freezing. And so what happens is that water drop then hits your car, your driveway, and it spreads out and then it freezes. And that's what causes that glaze ice, that clear ice that forms on everything, that pulls down the tree branches and just causes utter chaos and a complete problem. And so it really is just what's happening way up above you that you don't even realize. And with changing climates and with warming climates, we're seeing more of these warm air intrusions up at these mid layers of the atmosphere between where the clouds are and where we are at the ground, that causes some more interesting icing events for sure. So kind of a last little thing to leave you with about precipitation types that we see in the wintertime. So yeah, so there we go. There you have it. That's a summary of what I have to say about New England blizzards and snowstorms. So the types that happen and why they happen, the things that we're looking at, and what we're forecasting this year. So we've got, we can do a couple minute of questions then for you guys.
Yeah, thanks, Serena. That was so fascinating and also a little depressing. I'm not gonna lie.
I'm
I
sorry.
It's okay. And there are questions. And first, a lot of people were really, there was a lots of comments about your great graphics and how interesting the talk was. So I just want to make sure that you
Thank
see
you.
that.
Thank you.
And
Thank you.
yeah, lots of questions. And the first question came in from Rachel, and she was wondering about at what elevation do hills or mountains begin to disrupt storms? And is that common?
Yeah. That's a good question. And that can vary. It can vary on the different types. I mean, just look at the hills that you have around Hancock, right? Around the Harris Center and around Dublin. You have, we're near Monadnock, and that is definitely serious enough to impact the weather. But even just some of the smaller hills around there, 2 years back to back with a tornado in Dublin. Okay, like it's very interesting the way the meteorological conditions line up. Um, so they absolutely have an effect, and they doesn't have to be Everest. I mean, Monadnock absolutely affects the weather. Washington generates its own weather. Crotched Mountain weather goes around. I mean, and that's at 2,000 feet. You know, that's not nearly the height of the Monadnocks. So mountains absolutely have a tremendous effect on weather.
Fascinating. So interesting. Here's a question from our very own Michelle, and I wondered about this too, and I see some other people giving the thumbs up to this question is, do you have any weather apps or websites that you think are most accurate, and do you have any favorites that you would recommend?
Ooh, um, let's see. I think so. Where I tell everybody to go is to weather.gov. It's the National Weather Service. And I think they do the best job with weather forecasting because there's a lot of different apps out there and a lot of free apps. And um, the problem is you don't have meteorologists working behind the scenes on almost any of those apps. And so you have to ditch the mentality that it needs to be easy to get to and quick and give you just a number and a graphic because it's actually oversimplifying things and not doing us any favors. If you go to weather.gov, it's the National Weather Service. They have like 128 forecast offices across the country. They're looking at all the different forecast models. They have degrees in meteorology, masters, PhDs in meteorology. They live in those areas. They will tell you where the models are wrong. I mean, our meteorologists in the Great Main area will tell you exactly how forecast models do not do well with the Connecticut River Valley, and they will tell you exactly how and why. And so when you get a forecast from the National Weather Service, they have changed it. They have figured out what models work better than others. They're able to weigh them and balance them and actually go in and manually make changes to that forecast. And you can get a forecast at about a half-mile resolution with the National Weather Service made by a meteorologist. And they underscale those small scale dynamics about where you are, have the most accurate forecasts out there, know the most about the forecast models. It's just absolutely my favorite place to go for the general public to get weather information.
That's great. Cyrena, I like watching your weather information on Instagram, and I just want to give a shout out to that. So maybe you could tell us where we can find you on Instagram.
Yeah, so I'm on almost all the socials now. Everything's at WX Cyrena, WXCYRENA. So TikTok for however long that survives, Instagram, Facebook, Blue Sky, YouTube. And so I do. And so I do personally do some New England forecasts when the weather allows it. So you know, if the weather is necessary of talking about, I'll throw some stuff up there from time to time.
That's cool. Yeah, I do enjoy it. All right, this is a complex question from Renee. Can you speak to the changes happening in the Atlantic conveyor belt due to climate change? They've read that there's conflicting things over the years, so they've read some conflicting information about it. They're wondering about the cold water that is supposed to be circulating north and that maybe it's warming. And what does this mean?
Yeah, this is a question more for an oceanographer than a meteorologist, but I am familiar. And what I can tell you is there's mixed results in the models, and there are questions as to what's going to happen because you do have this kind of conveyor belt once again because of these differentials. The reason you have the currents that you do are because of where the warm water is versus the cold water. And so you have a constant cold water supply source from the north and warm from the south. But if you start getting a breakdown in those differentials, think of our high and low pressure cylinders. If they're here, that wind's going to be really strong to balance them out in that tube. If they're here, is it going to be as strong? And the same thing happens with temperature differentials in our atmosphere and in the oceans and all that. Because don't forget, actually, our atmosphere is a fluid, believe it or not. And fluid dynamics applies to ocean meteorology versus or oceanography, just like meteorology. It's all a fluid and it all acts the same. Um, the lower the differentials, the smaller the currents, the smaller the winds. And so there's definitely some interesting research behind if we, you know, lose Arctic sea ice, if with the increase, you know, if we get a lot, you know, with the melting and every year you get less melting because there's less ice to melt from and it's less water in there and less of a differential. What is that going to do? It's a huge question. I don't have an answer. It's a massive question.
Yeah. All right. Well, there's a part two to this, and this one's
Ooh.
really interesting to me. They're also wondering, is it possible that climate change or something in our changing environment potentially can cause the conveyor belt to slow? And then if that happens, would we actually see an ice age? I was like, what?
I know. Yeah, once
Very
again,
good
that's like
question.
good oceanographer question. That's I have no problem saying when that's above my knowledge, and I would wish I could answer that for you because that is super interesting. I know I've heard uh hypotheses about such things. I cannot speak to them in an educated way, but it's yeah,
Yes.
I've heard the same things.
Sounds like if people are looking for something to do on those icy days, you could do a little bit of reading on your own about this.
There you
And
go.
there is another great question too from Renee, and I like this was
Go
interesting to
Renee.
me. I know. What are your thoughts on human manipulation of clouds to increase precipitation in drought-stricken places? And is this common and is it effective?
Gotcha. Common, no. Effective, no. So cloud seeding techniques are very interesting. And so the reason cloud seeding has been tested for a long time, long, long time. And so what they're actually doing with cloud seeding is in order for water to go from the gas form as water vapor to a condensed form, liquid, it actually needs something to condense on. It needs a condensation nuclei. And actually, in my most recent book, we talk about it because that's a really critical part of a hurricane formation, where you get Sahara dust that blows over a warm, humid ocean actually causes condensation nuclei for that warm, humid ocean water to form water drops on which forms the first clouds that can turn into hurricanes. So they've taken a similar concept and said, we're going to apply that same thing for cloud seeding. And so there's research behind cloud seeding, and it's been practiced in a lot of ways too. So airports, I know back in like the 70s, my mom's sitting over here and I'm looking at her because I remember my dad telling me stories about how they would clear the fog over runways with like cloud seeding, drop some dry ice over them and, you'll get the fog to evaporate away. And so we know that it can work in some limited areas like that and can be helpful for airports. As for increasing precipitation, it's a really interesting thing. The research shows it has a negligible to at best 10% ability to increase precipitation. So it's really small. And so what they're doing when you do cloud seeding is they're taking naturally occurring chemicals in the atmosphere and creating a condensation nuclei, something for a water drop to form on to then precipitate and fall out of a cloud. And so unfortunately, it's not great. There's some really bad misinformation floating around on the internet about it, especially with a big storm that happened in the Emirates, Dubai, somewhere like that, where they were like, "Oh, cloud seeding." No, it was actually very well forecast. It was a very unusual storm. Those forecast days in advance had nothing. Cloud seeding can't cause that kind of flood. Um, so unfortunately, it's not amazing. Not great results with it, not very effective, and there's limited research behind it, but there is some. Something that is kind of interesting that was similar is that there is some studies being done about how crops can increase clouds and precipitation. So actually, by having crops versus bare land, actually introduces a little more water vapor into the system. And so there is some research. And once again, the correlations are loose. And so we're talking a negligible to 10% difference. But where certain crops are planted could actually create clouds more prominently over some locations than others because of how they change the water vapor balance. And, think about how the sun shining on bare brown ground is going to be warmer and less moisture in it than over a crop where it's green, it's absorbing some of the heat, some water vapor is getting released in the atmosphere. You're just getting some different circumstances. And so there's some interesting studies being done about how that affects our weather. But once again, it's not a lot. See, and I see in the comments, rainforests do, rainforests absolutely do. So there is absolute science about how very large areas of forest create their own precipitation through the water vapor that they emit, which rises and cools and precipitates back down again. And it's a beautiful part of the water cycle. So nature almost does it better than people do.
Yes, that's so true for so many things.
Yep.
I think we're just about out of time, and I just wanted to thank you, Serena. That was such a great talk. It was so rich with science and information, and people really enjoyed it. And
Great.
yeah, hope to see all of you at some of our other Harris Center Zoom events or in person. And let's give Serena just a big thumbs up for being such a great presenter and so informed and smart. Yeah,
Awesome. Thank you
thank
guys so much. I
you.
really love being here. I love the Harris Center and love everything you guys do. So um, this was great. Thank you for having me.
All right, right back at you, Serena. All right, and good luck with everything. And everybody, make sure you get some micro spikes. It sounds like we're going to need ice grippers and not snowshoes. Wah, boo.
Yeah. Yep. There you go. Awesome.
Okay. All right,
Thank you
take care.
guys.
Happy holidays to all.
All right.
Bye.
Bye.